Hello, my name is Jonathan Blank, a PhD student in the Neuromuscular Biomechanics Lab and the Biomechanical Advances in Medicine Lab at the University of Wisconsin-Madison. Today I'll be presenting to you my poster, The Effects of End-User and Design Parameters on Shear Wave Propagation, a high-throughput parametric modeling study. Shear wave tensiometry is a measurement technique developed in our lab to track tension in tendon and ligaments based on the tissue's shear wave speed, which is proportional to the tissue's stress. While handheld and wearable tensiometers are useful tools to measure shear wave speed, the measurement may vary from user to user depending on their tensiometer design or how they hold or affix a tensiometer superficial to the tissue of interest. We have developed a parametric model of handheld tensiometer to study the effect of these end-user parameters on the measured shear wave speed. Hence, the objective of this study was to characterize the effect of these end-user parameters on measured shear wave speeds using a handheld tensiometer. Our parametric finite element model consists of a transversely isotropic collateral ligament and a multibody tensiometer. The tensiometer was modeled as a set of 3 rigid bodies corresponding to the tapper and 2 in-series accelerometers. The tensiometer mass was modulated by changing the mass of the rigid bodies, the internal stiffness was represented using a spring damper, and finally, the application force was changed by changing the displacement of the rigid body components into the ligament. The shear wave speed of the loaded ligament was measured using a correlated time delay of the tapper-excited shear wave passing the 2 accelerometer bodies. We ran 3,000 Monte Carlo simulations in total on a high-throughput computing grid while varying the tensiometer mass, internal stiffness, and application force, which returned over 1,400 successful jobs at 2 different ligament strain levels. While we did not detect a significant relationship between the shear wave speed and tensiometer component mass or stiffness, the simulations at 6% strain showed a strongly linear relationship between the tensiometer application force and the measured shear wave speed, which corresponded to a 0.93 meter per second increase in wave speed for a 1 Newton increase in application force. Furthermore, higher application forces corresponded to a higher local stress at the measurement location in the ligaments. Since shear wave speed scales with the axial stress in tissues, this could be a causal mechanism for the higher measured shear wave speeds during higher tensiometer application forces. In conclusion, this model demonstrates that the user application force may have an effect on shear wave speeds measured using a tensiometer. The next steps in this research are to characterize the effects of tensiometer application force on shear wave speeds experimentally ex vivo, and also to translate this sensor into orthopedic applications.